So we did all that work and we got the symmetries of our 2p salts, right? And so what are we doing, right? We are combining, the y, the x, and the z p orbitals in different linear combinations. And we found that the symmetries of those different linear combinations are as follows: sigma g plus, pi g, sigma u plus, pi u. And we started with 6 atomic orbitals. The total degeneracy, or the total number here, is 6, right? We have 1 here, 1 there, 2 in each of the pi's. So that's all good. And so now we have to figure out how these things look like. And again, we'll get to this in chapter 6. We haven't quite done it yet, but you can use the projection operator, which I said this earlier in chapter 5, is a tool for allowing us to visualize things. One of the things that it allowed us to visualize, it's a mathematical tool. One of the things that allowed us to visualize were the motions of stretches and bends in vibrational spectroscopy once we have the symmetry. And we could do the projection operator all just using group theory, right? Same thing is here, true. Here, I'm just gonna give you them. I mean, you can actually probably guess and try to draw the p orbitals in different ways and then check their symmetries. And you should be able to show me that this salt does have sigma g plus symmetry. I'm telling you that. Later on in the course, chapter 6, we'll use the projection operator to show the picture of the salts. So we'll get there, I promise you. It's a good deal of work. So, this is already a pretty long problem. So I don't want to do that on such a long problem to begin with. Anyway, there's a sigma g plus, there's a sigma u plus. And let's just do one of these, let's try to figure out, why is this sigma u plus? Why is the symmetry actually sigma u plus? So I'm going to go back to the slide with the character tables. D infinity 8 character table here. Okay, there we go. And so we have a Salk, I'm telling you, looks like that, right? And of course, the central atom's right there. So if we do an E on that, when we think it's sigma u plus, okay. If we do an E on that, we're gonna get it back. If we do a C infinity on that, that's rotating through there. That's gonna do nothing, right? We're going to, if we do a C infinity, that's gonna do nothing. So we get back the same picture, so we get a 1. If we do any mirror plane on it, vertical mirror plane, we could choose one that just cuts right through the molecule like this. That's not going to do anything. The top of the white's going to go to the bottom of the white, top of the black's going to go bottom of the black. So any mirror plane here is going to get you back the same thing. So that gets you a 1. Now you do inversion. Okay, inversion, that's an interesting one. Inversion, that takes left to right and right to left. So on the far left is white, and that's going to turn into black there. So right, that goes over there. And on the far right, that's going to become the far left. And then kind of the middle, closer left here is now going to be the right. Okay, and then same thing with this other side. So you can see that one is a negative of self, so you're going to get a -1. If you do a S infinity, do an S infinity, what's that? That's a C infinity. That does nothing, but then it's a sigma H. And so sigma H is going to flip everything. So that's going to get you a -1. And then lastly, you're going to do a C2. And so that's doing 180 degrees. That's very similar in this case to a mirror plane. It does the same thing, it flips everything, right? So that gets you a -1. So don't forget, in order to get the symmetry of any molecular orbital, you have to check its symmetry. This isn't a molecular orbital yet, this is just a Salk, we're just checking it. We'll derive it with the projection operator. All right, so now we're back in business. So I'm just going to show you the other ones. There's pi u. There's two of them because they're degenerate, and pi g. Now, we have total, our oxygen salts. Don't forget, we had our 2s salts, right? And we now have our 2p salts. Now we have to look at our carbon atomic orbitals. What's available for bonding in carbon? Well, it's a second row element, 2s atomic orbitals and 2p atomic orbitals. Where did I get these symmetries from? Why is 2s called sigma g plus? Well, it's a sphere. It's s orbital. Orbitals are always the totally symmetric representation. One's across the board. For t infinity h, that's sigma g plus. 2p's, where did I get that? Sigma u plus pi u. Well, look at the x, y, and z vectors. The p orbitals transform. Px transformed as the x vector. Py transforms as the y vector. Pz transforms as a z vector. So the pz orbital is going to transform as sigma u plus. The x and the y transform together as pi u. Now I have to look at the energies. I got the symmetry. I know that orbitals of same symmetry and similar energy are going to mix. So I look up the ionization energies for the 2s and the 2p's, just get it straight from the table. That gets me the atomic orbital energies. I can plot that along with the symmetries. There's the energies. Here's carbon. Here we have the 3 2p's, the 2s. Here we have the 6 different salts. Put those down. And here's 1, 2, 3, 4, 5, 6, right? And here are the 2s salts. And now we go for it, okay? So the first thing to see is that these 2s salts are pretty low in energy. They're negative 32. And, you know, especially in light of the fact that there's other stuff closer in energy here, we're going to call these non-bonded. Now, how do you know if low is too low? We'll talk about that in detail in chapter 6. But right now, you know, I'm just telling you low is too low. This is greater than, greater than 10 EV? That's a lot, okay? So technically, you could have some bonding here between the 2s, right, sigma g plus and sigma g plus, but it's not going to be a lot. More likely, most of your bonding is going to be sigma g plus here and sigma g plus here. So they're more similar in energy, right? 15.9 and 19.5. So the best representation is just to call these non-bonding. All right, so these would just move straight over. I have them splitting here, but in reality at this point, they're just moving straight over. I put them splitting just so you could see them, okay? It's just for pictorially. But really, they're just moving straight over. They're at negative 32.3. They're not moving. All right, so now let's do that interaction we talked about. Sigma G plus, the 2s, with the sigma G plus. We're gonna make a bonding interaction. The sigma G plus was this one. Refer again to the previous page where I had them all out, okay? The symmetries. And I told you that we could check which one is which, and again, use a projection operator to find out what the salts look like. But you can see you can make a bonding interaction where you have, you know, these light colored lobes overlapping, and you're gonna have to do some opposite thing to make the anti-bonding interaction. There, here I made the s orbital dark, and there you have a node and a node. And so call it with a lowercase letter because it's a molecular orbital, lowercase sigma, it's sigma G plus, and we have sigma G plus star. How did I find sigma G plus? I had to look at this and translate it, go through all the symmetry operations, d infinity h, and figure out how it translates, okay? And it turns out it has symmetry sigma G plus. All right, sigma u plus with sigma u plus salt. So sigma u plus, that was the pz orbital. There's a bonding interaction. Flipping it, making the negative of it, there's the anti-bonding interaction. There's a node, there's a node. There's many nodes, right? But anyway, the ordering of all these things, you can use the nodal relationships, right? More nodes. This one has 1, 2, 3, 4, 5 nodes. 1, 2, 3, 4, 5 nodes. This one has 1, 2, 3, 4 nodes. You can use the nodal relationships to help you. You can also use the fact that, hey, it came from a higher energy pz orbital, so it's going to be raised higher, okay, than this one. Similarly, this isn't going to go down below here because it came from a higher one. All right. Lastly, we got our pi u's. And so those were just p orbitals, or px and py's. And we have these pi's. And so we can put them all in phase here. That's going to be a bonding or anti-bonding if we flip the middle one. Okay, so that's basically everything. We have one last thing here, which is we used up our pi, sigma u plus, our pi u, our sigma g plus, and then from here, we already counted for these. We said they're non-bonding. I put the ends there, and then we use sigma g plus, sigma u plus, and we used up our pi u. We did not use our pi g yet. Pi g doesn't have anything to bond with. There's no pi g's over here. So we just slide that over. That's going to be non-bonding orbital. Slide it over, no electron density on the carbon, just leaving it blank there. Populate in the electrons. You're at carbon. Carbon has 4 valence electrons. You're at oxygen. There's 2 of them, good for 6 each. That's 12. 12 plus 4, that's 16. 2, 4, 6, 8, 10, 12, 14, 16. There we are. How many bonds do we have? These are non-bonding. Bonding, 2 electrons, 4 electrons, 5, 6 electrons, 7, 8 electrons. 8 electrons are in bonding. 1/2, 8 minus 0. There's no anti-bonding here. The anti-bonding, there's some non-bonding, right? And so that's going to get you 4 divided by 2, 2 double bonds, because, well, there's bond over, total bond over 4, but it's delocalized over 2 bonding sites, right? So good for 2 double bonds, as the Lewis structure of carbon dioxide would suggest. One last thing, you can have mixing. And in fact, you do have mixing. In both of these cases, right, and this is where you'll get some S character in these bonds, like this molecular orbital will have some S character because this sigma U plus can mix with this 2 sigma U plus. So that's how these orbitals kind of get into play. Same thing with this 2 sigma G plus can mix with this 1 sigma G plus. Remember these numbers here in the front, it's just counting, you know, on your diagram, what number in order of energy of orbital you are. So this is the 3rd sigma U plus that exists. Here's the 2nd, here's the 1st, okay? So just counting. So anyway, that is it, guys. That's a more complicated example. We use p orbital salts, we use s orbital salts. You could do d orbital salts. You know, imagine you had some transition metal cluster, like you wanted to do the molecular orbital theory of like some gold cluster, right? And you might have learned, like, maybe you've seen this before, like there's stable gold clusters, like there's all sorts of different ones with multiple atoms. Well, now you have a situation where you could have S salts, P salts, and D salts. And so, you know, using the skills that we've learned, it would be really painful, but you could go calculate all those D salts and P salts and, you know, use group theory, and if you need the point group and everything, and try to figure out, you know, what's a reasonable MO diagram. So I think that's pretty cool. You know, this is a more complicated example, good for homework, too complicated for exams. And so please, you know, come to office hours, come to class, and we can discuss any of this in as more or less detail as you want. All right, and I'll see you at chapter 6.